Welcome back to che531. In this video, I'll be talking about Newton's method in multi-dimensional cases. So we learned about Newton's method in one-dimensional case where we iteratively solve for the unknown x using equation like this. So for every initial guess xi, we find the next initial guess xi plus 1 using this equation where delta x is the change in x at every iteration, and this delta x was found through solving a linear system. Well, in the case of 1D, actually it's just one equation, but in case of multi-dimensional case or multi-dimensional variable, this is going to be a matrix. So anyways, in one-dimensional case, we had f divided by f prime of x, or f of x divided by f prime of x. In multi-dimensional case, we're going to have f, or vector f, basically, well, reading it from left to right is going to be the Jacobian, which we're going to talk about in a minute. Jacobian / f. So what is Jacobian? Well, Jacobian is matrix which looks like this. Imagine we have n equations to solve, and for every equation we have n variables, right? So the number of equations should match the number of unknowns. So if you have n equations, we can have at most n variables. Okay, so for every equation, we get the derivative of, let's say, the first one with respect to the first variable, derivative of the first function with respect to the second variable, derivative of the first function with respect to the third variable, and all the way down to derivative of the first function with respect to the nth variable. So that's going to be the first row of the Jacobian. And similarly, the second row of the Jacobian is going to be the derivative of the second function with respect to x1, the derivative of the second function with respect to x2, with respect to x3, all the way to with respect to xn. So this is all about the second equation. So you keep going like that, and then the last equation will be the derivative of fn with respect to x1, derivative of fn with respect to x2, all the way to derivative of fn with respect to xn. Okay, so we have this matrix, which is Jacobian, times the change in x, well, x1, x2, all the way to xn, and that's equal to the f values. Okay, in short, we can write this matrix equation in this form, where the variables at I plus 1 iteration is equal to the variables at I iteration minus the change at the ith iteration. Okay, so how do we solve for the change? Well, it's basically you have to solve this system, and we know that to solve a system, we never use inverse or determinant or stuff like that. We have to use the backslash operator. And the backslash operator is, if I want to solve for this, then it's going to be the matrix backslash the right hand side. And that's what it is. So the change in x is going to be the matrix, which is the Jacobian, backslash right hand side, which means this vector. Okay, what is the convergence? Well, the convergence is, we're going to look at, now we have n variables, right? For every variable we have a delta x, like in this case we have n delta x's, so the convergence will be the change in delta x for every row divided by the current value. So let's say the current value is this, right? That's, we're sitting at ith iteration. This is the current value, this divided by that, gives you the tolerance for the first variable, this divided by that, tolerance for the second variable, and so forth. So by dividing this, we're going to find the maximum of all, which is going to be the only tolerance we use for the whole iterations. So we're not going to have n tolerances, we're going to have just one tolerance, and that's going to be the maximum of every delta x divided by corresponding x. We can check this actually at every iteration. So here's the flow chart. Okay, you're going to start with the initial guess, and because this is a multi-dimensional variable problem, we're going to have n guesses, right? So for every x, we have to have a guess. So that's why we have this x vector, which means we have to guess the whole vector. Okay, So after we guess the x, we're going to go and find the Jacobian in the right-hand side. Solve for the delta x in the current iteration by using j_f. Then update the variable. So this is the updated variable, this is the current variable, that's the change. Then we're going to find the maximum tolerance, or maximum change in every variable. And this should be less than tolerance. If this is not less than tolerance, then we add to the iteration, we go next iteration and repeat from calculating the Jacobian. Okay? And if this tolerance is less than, if the delta x divided by x is less than tolerance, that means we already converged. So that's the yes, and that's the stopping point. Okay. So for Newton's method, the very important point is that the initial guess, or initial guesses for variables, should be close enough to the root. And if it's not enough, it's not close enough to the root, then the method is not going to converge. In other words, it's going to basically diverge. Okay, so I think that it's a good time to look at one example of how we can do Newton's method before we dive into built-in linear equation solver. Okay, so here is one example of Newton's method. It's let's say I want to solve a two-dimensional problem. Okay, and let's see, I think, do I have an example here? Yeah. So let's look at maybe this problem. Let me just double check to see if we're basically looking at the same script. Yes. So the problems that I'm trying to solve is x1 squared plus x2 squared minus 36 equal to 0. Okay. So basically I'm solving these two equations. One important note to keep in mind is if you have an equation like this, to use Newton's method, you have to move everything to the left side. So the equation should be something equal to 0, not like x1 squared plus x2 is equal to 36. You cannot do that. You have to move everything to the left and set it to 0. And same thing for the second equation. And that's why I have my function set up like this. Okay, the first equation is x1 squared plus x2 squared minus 36. And this is, the equality, the equal to 0 is actually implied. So we never write it at like this thing equal to 0. We just write the left side and leave the right side as an implied. Okay, so we're going to imply that the right side is 0. Where the second equation is x1 squared minus 3x2 minus 16 equal to 0. And that's what this equation is. Okay? Alright, so this is, or these are the equations. Then we get the first equation and find the derivative of the equation with respect to both variables. Derivative of this with respect to x1 is going to be 2x1. And that's when I have my first row of Jacobian. Derivative of this equation with respect to x2 is going to be 2x2. So I'm done with the first equation. Then we go to the second row and take the derivative with respect to x1, which is 2x1. Derivative of this equation with respect to x2 equals minus 3, and that's it. So this is going to be my Jacobian. It's a 2 by 2. My function outputs, well, this subfunction actually, this func x outputs f in the Jacobian. Okay. All right. So now let's go back to the beginning of the code. Well, initially I set all the variables to 0. I close all the figures and clear the screen. My dimension is 2 because the problem that I'm looking at has only 2 variables. Alright, so I'm going to start the initial guess of 10, 10 on x and well, on x1 and x2. Maximum iteration is 100, and tolerance is 10 to the 7. I get my headers as before. I'd like to see iteration, count, the maximum relative error, and the norm of f. And you know what norm means here. This is norm 2, and f is the right-hand side of my equations. Or basically, well, if you get the root, then f is completely 0 in every element, but because initially we don't get the root, the f is non-zero overall. Okay, so we set the flag to 0 as before. That means if flag is 0, we converge, and if flag 1 is a diverge scenario. Okay, so we have a while loop, and we have to iterate as long as the relative error is bigger than tolerance. In every iteration, we're going to find the Jacobian in f by calling this func that we saw before. And I'm going to find my delta x, which is Jacobian /f, exactly like the equations I had up here. This is it, right? Or basically this is it. Delta x is equal to Jacobian /f. And that's what I have here. That's delta x. Then the relative error would be maximum of absolute value of delta x divided by x, but because I have n delta x values, I just do the dot operator, okay, which means I get n of these values, delta x by x, and we find the maximum of them. As soon as we get the delta x and relative error, we can update our x, which is going to be the current x minus delta x, exactly like this equation right here. And then we're going to check the maximum number of iteration. If the n step is equal to the maximum number of iteration, that means we already hit the maximum number of iterations. We have to quit, and we set the flag 1. And if we don't meet this condition, that means we didn't hit the maximum number of iteration, and flag will be 0 by the time we come out of this while loop. Okay, so flag 0 means solution is found. We print the solution with this format, and that is it. I'm going to go ahead and run the code, and there you go. So you see that in 6th iteration I get the solution. That's a vector of 5.06, 2.21. So this is x1, this is x2. This is maximum relative error. You see that it's going down quadratically, almost very close to the solution. So, well, yeah, you see that the quadratic, well, in this case, the error actually gets squared every time we go to the next step, maybe from this point on, right? So this one is a square of that almost. Look at the order. This is -3, -6, -12. This is exactly quadratic. And norm of f is also going down very fast. So norm of f is 4, next step is 0.1, 10 to the -4, oops, right here, and then 10 minus 10. You see how fast it gets to the root very quickly. Okay, so that was Newton's method. In the next few minutes of this video, I'll be talking about the built-in functions in MATLAB to solve the root of multidimensional problems. Alright, so let me get into there. Okay, there are two functions that mainly we can use. One is fsolve that we saw before in the previous video, and that is basically to solve not only numerical values but also symbolic. Fsolve actually is for system. I'm sorry, actually fsolve is just for numerical, to find the root of a function numerically. And solve is to basically solve the system symbolically. That's why for solve we do not have initial guess, but for fsolve we do have initial guess. Okay, and I think that is it. So let me get to here and see if there's an example we can do for multi-dimensional cases. Alright, so this is one example, and that is we have a system of two equations, two unknowns. That's the first equation, x1 squared plus x2 squared minus 17 equal to 0. The second one is 8 times x1, well, third root of that, plus x1 square root minus 4 equal to 0. So in the next video, I'm going to show you how we can solve this system using fsolve in MATLAB. Thanks for watching, and stay tuned for the next video on solving linear system using MATLAB.